Let's visualize a finite segment of the number line, ranging from -5 to +5. This represents a small portion of all possible numbers. We'll label the integers from -5 to +5. Notice how these numbers are evenly spaced, representing the discrete nature of integers on our continuous number line. Now let's add arrows at both ends. These arrows symbolize that our number line doesn't actually stop at -5 or +5, it continues in both directions. Watch as we extend our number line. This animation represents a key aspect of infinity. No matter how far we go, there's always more. The number line stretches endlessly in both directions, encompassing all real numbers. As our number line extends, we approach the concept of infinity. On the left, we have negative infinity, and on the right, positive infinity. These symbols represent the idea that numbers continue without end in both directions. We're highlighting these infinity symbols to emphasize a crucial point. Infinity is not a number, but a concept. It represents the idea of endlessness, of always being able to go further or add more. This number line demonstrates a fundamental property of the real number system. It's unbounded. Between any two numbers, no matter how close or far apart, there are infinitely many more numbers. And beyond any number, no matter how large or small, there are always more numbers stretching towards infinity. Imagine a hotel that stretches infinitely to the right. This is our hotel infinity, a thought experiment that helps us explore the fascinating concept of countable infinity. The rooms in this hotel are numbered from 1 onwards, continuing infinitely. We can see the first few rooms, but remember, they go on forever, illustrating the concept of a never-ending sequence of natural numbers. Let's start with 5 guests occupying rooms 1 to 5. This represents a finite number of guests in our infinite hotel. Now, what happens when a new guest arrives? To accommodate the new guest, we simply ask each existing guest to move to the next room. Guest in room 1 moves to room 2 to 3, and so on. This shift is possible because we have infinitely many rooms. The new guest can then occupy room 1. This demonstrates how infinity allows for seemingly impossible accommodations. Now, let's consider a more challenging scenario. Imagine a bus arrives with infinitely many new guests. How can our already full infinite hotel accommodate infinitely many more people? This might seem impossible, but with infinity, we can find a solution. Here's the ingenious solution. We ask each existing guest to move to the room number that is double their current room number. So the guest in room 1 moves to room 2, the guest in room 2 moves to room 4, and so on. This applies to all guests, even those in rooms we can't see. By moving all existing guests to even-numbered rooms, we've freed up all the odd-numbered rooms. Now, we can accommodate infinitely many new guests in these odd-numbered rooms. The first new guest goes to room 1, the second to room 3, the third to room 5, and so on, infinitely. This remarkable property of infinity shows us that even when an infinite set seems full, we can always find room for more. It challenges our intuition about numbers and space, illustrating the unique and sometimes counterintuitive nature of infinite sets in mathematics. Let's begin our exploration of countable infinity with a number line spanning from -5 to +5. We'll now highlight the positive integers from 1 to 5 with red dots. These represent the natural numbers, which form the basis of countable infinity. On the left side of the screen, we'll create a list. This list will demonstrate how we can systematically count these numbers, a key aspect of countable infinity. We're now connecting each number on the line to its corresponding position in our list. This one-to-one correspondence is crucial in understanding countable infinity. To illustrate that this process continues beyond what we've shown, let's extend our number line to display more positive integers. This extension represents the infinite nature of the natural numbers. We'll continue our list up to the 10th number. Notice how we can keep counting indefinitely, assigning each natural number a unique position in our list. The ellipsis at the end of both the number line and the list signifies that this process continues infinitely. No matter how far we go, we can always count the next number, demonstrating the essence of countable infinity. This concept we've illustrated is known as countable infinity. It's called countable because we can establish a one-to-one correspondence between the natural numbers and the elements of this infinite set. We've demonstrated how we can systematically count all positive integers, showing that even though the set is infinite, we can still enumerate its elements in a well-defined order. This property distinguishes countable infinity from other types of infinity and forms the foundation for understanding more complex infinite sets in mathematics. Let's visualize the concept of infinity on a number line. This line represents a small portion of the infinite number line, stretching from 0 to 5. The blue dots represent the natural numbers from 0 to 5. These are the counting numbers we're all familiar with, forming a discrete countable set. Now, let's consider the real numbers. In red, we've shown just a few examples between each pair of natural numbers. For instance, between 0 and 1, we have 0.5 and 0.75. These represent only a tiny fraction of the real numbers in each interval. To better understand the density of real numbers, let's zoom in on the interval between 1 and 2. This yellow rectangle highlights our area of focus. As we zoom in, we can see more real numbers. Our number line now shows increments of 0.1 between 1 and 2. But even this is just scratching the surface of the real numbers in this interval. The remarkable property of real numbers is that between any two real numbers, no matter how close, there are infinitely many more real numbers. This property is called density. For example, between 1.1 and 1.2, there are infinitely many numbers, like 1.15, 1.155, and so on. This infinite density leads to a profound mathematical truth. The real numbers are uncountable. Unlike the natural numbers, which we can count one by one, the real numbers cannot be put into a one-to-one correspondence with the natural numbers. This means there are more real numbers than there are natural numbers, even though both sets are infinite. The contrast between the countable infinity of natural numbers and the uncountable infinity of real numbers illustrates a fundamental concept in mathematics. Not all infinities are the same size. Some infinities, like that of the real numbers, are larger than others, such as the infinity of natural numbers. Cantor's diagonal argument is a fascinating proof that demonstrates the existence of different sizes of infinity. Let's explore this concept step by step. We begin with a list of random decimal numbers between 0 and 1. These represent a subset of the real numbers in this interval. In theory, we could try to list all the numbers between 0 and 1, but Cantor's argument will show us why this is impossible. Now we highlight the diagonal digits in red. Notice how we're selecting one digit from each number, forming a diagonal pattern across our list. This is the key to Cantor's ingenious argument. Here's where the magic happens. We construct a new number by changing each highlighted digit. If the digit is 5 or less, we add 1 to it. If it's greater than 5, we subtract 1. This ensures our new number is different from every number in our list in at least one decimal place. These yellow arrows show how each digit in our new number corresponds to a changed digit from our original list. This visual representation helps us see that our new number is unique and different from all the numbers in our list. So what does this new number mean in the context of infinity? Let's examine the implications of what we've just done. The new number we've created is guaranteed to be different from every number in our original list. Even if our list were infinitely long, we could always use this diagonal method to create a new number not in the list. This proves that there are always more real numbers than can be listed, no matter how long the list is. In mathematical terms, we say that the set of real numbers is uncountably infinite. Cantor's diagonal argument reveals a profound truth about infinity. Some infinite sets are larger than others. The set of real numbers is larger than the set of natural numbers, even though both are infinite. This concept of different sizes of infinity revolutionized our understanding of mathematics and set theory. We're going to explore a fascinating function that helps us understand the concept of infinity. This function is f of x equals 1 divided by x. Let's visualize it on a coordinate plane. Here's the graph of our function. F of x equals 1 divided by x. Notice its unique shape. It starts high on the y-axis and then curves down, getting closer and closer to the x-axis as we move right. This behavior is key to understanding limits and infinity. Let's label our axes. The horizontal axis represents x, and the vertical axis represents y, or f of x in this case. We'll start with a point at the coordinate 1, 1. This point represents when x equals 1 and y, or f of x also equals 1. 1 divided by 1 is indeed 1. Now watch closely as our point moves along the curve. As x increases, getting larger and larger, y, which is 1 divided by x, gets smaller and smaller. This illustrates a fundamental property of fractions. As the denominator grows, the fraction itself shrinks. The red dashed line represents what we call a horizontal asymptote at y equals 0. Our function will get infinitely close to this line, but will never actually touch it. This is because no matter how large x becomes, 1 divided by x will always be a positive number, albeit an extremely small one. This mathematical notation expresses what we've been observing. It reads the limit as x approaches infinity of 1 over x equals 0. In simpler terms, as x grows infinitely large, 1 divided by x gets infinitely close to 0. Let's focus on how the y-coordinate of our point behaves. As x continues to increase, y keeps getting smaller, approaching 0 but never quite reaching it. This arrow highlights this downward trend. This visualization demonstrates a key concept in calculus, the idea of a limit. Even though we can't physically reach infinity, we can describe the behavior of our function as we get closer and closer to it. In this case, we can confidently say that as x grows without bound, f of x approaches 0.